Welcome. In this lecture, we are going to build the 2 to the k factorial design from the ground up, learning how to code factors, why orthogonality matters, and how to extract clean effect estimates from a structured experiment. By the end, you will be able to look at a factorial data table and immediately know which factors drive the response, which combinations matter, and where a simpler approach would have led you astray. We will do all of this through a single running example that we carry from the first slide to the last. Let us start with the method most experimenters reach for first, varying one factor at a time, or OFAT. The idea seems sensible. Hold everything fixed, change one thing, observe what happens, then move to the next factor. The problem is fundamental, not cosmetic. When factors intersected, when the effective temperature depends on how long you bake, OFAT never sees that. It explores a thin slice of the experimental space and draws conclusions about the whole space from that slice. The result is that the OFAT recommendation can point you to a combination that was never actually tested, and that combination may not be the true optimum. The factorial design, by contrast, tests every combination simultaneously, so interactions are visible rather than assumed away. Here is the experiment we will carry through the entire lecture. A food scientist wants to understand what drives the crispness of a snack cracker, scored on a 0 to 100 scale. 3 factors are under investigation: oven temperature at 160 or 200 degrees Celsius, baking time at 20 or 30 minutes, and fat content at 10 or 20%. A fully replicated 2 to the 3 factorial is used, meaning every one of the 8 factor combinations is run twice, giving 16 total runs. Looking at the data, you can see the 8 combinations listed in order, with both replicates and the cell mean. Run 1, the lowest settings on all 3 factors, gives a mean crispness of 46. Run 8, the highest settings on all 3 factors, gives a mean of 73. The client's questions map directly onto this structure. Main effects will tell us whether each factor matters on average across all conditions. Interactions will tell us whether factors must be set jointly rather than independently. Every question the scientist has is answerable from this single 16-run experiment. Before we can estimate anything, we need a systematic way to list all the combinations. That is what Yates' standard order provides. For k factors each at 2 levels, there are 2 to the k combinations. Yates' order lists them by cycling the first factor fastest, alternating low and high on every run, cycling the second factor next fastest, and so on, with the last factor changing only once, halfway through the list. This is not just a bookkeeping convention. It ensures no combination is accidentally omitted. It makes the design reproducible. Any 2 experimenters anywhere will write the same table, and it sets up the coding step that comes next in a completely natural way. Let us apply Yates' order to the cracker experiment. We have 3 factors, so 8 combinations. Temperature cycles fastest, low, high, low, high, low, high, low, high, low, high. Baking time cycles next, 2 lows, 2 highs, 2 lows, 2 highs. Fat content cycles next, 2 lows, 4 lows, then 4 highs. Written out in natural units, the 8 runs go from 160, 20, 10, all factors at their low levels, up through every combination, ending at 200, 30, 20, all factors at their high levels. This systematic listing is the skeleton of the design, and everything that follows hangs on it. Here is the Yates ordered table for the cracker design confirmed. Notice the pattern in each column. Temperature alternates on every single run. That is the fastest cycling factor. Baking time switches in pairs, 2 lows, two highs, repeating. Fat content holds low for the first 4 runs and high for the last 4, the slowest cycling factor. This regularity is not accidental. It is what guarantees that every combination appears exactly once per replicate, and it is what makes the design easy to communicate to a client or a production team without ambiguity. Any 2 people reading this table will run the same experiment. Now we transform the natural unit factor levels into coded values on a -1 to +1 scale. The formula is straightforward. Subtract the midpoint between the high and low levels, then divide by the half range, that is, half the distance from low to high. This centering and scaling does 3 important things. First, the intercept in the fitted model becomes the grand mean of the response, a directly interpretable quantity. Second, all effects are measured on a common scale, so you can compare the effect of temperature to the effect of fat content without worrying about the different units. Third, and most importantly, this transformation is what produces orthogonality, the property that each effect is estimated independently of every other. We will see exactly what that means in a moment. For the cracker experiment, the 3 coding formulas are x1 equals temperature minus 180 divided by 20, 22 equals time minus 25 divided by 5, and x3 equals fat minus 15 divided by 5. The midpoints 180, 25, and 15 are the averages of the low and high levels for each factor. The denominators 20, 5, and 5 are the half ranges. Applying these formulas to every run in the Yates order table converts each natural unit level to either -1 or +1. Here is the coded design alongside the natural units. Every coded column has exactly 4 -1s and 4 +1s, so each column sums to 0. That symmetry, 4 observations at each level, is the mechanical reason the intercept equals the grand mean, and the reason effects are estimated independently of one another. When you center a column on 0, it carries no information about the overall level of the response, only about the difference between high and low. That separation of information is what orthogonality means in practice, and it is what makes the 2 to the k design so powerful. Orthogonality is the central structural property of the 2 to the k design, and it is worth understanding precisely. 2 columns in the design are orthogonal when their element-wise dot product multiply corresponding entries and sum equals 0. The consequences at the corresponding effect estimates are statistically independent. Knowing the estimate of the temperature effect tells you nothing about the estimate of the time effect. There is 0 covariance between them. In practice, this means 3 things. Each effect estimate is unaffected by the others, so you can add or remove terms from the model without changing the remaining estimates. Every effect is estimated with equal variance, and that variance is the minimum achievable for the given number of runs. Orthogonality is not a luxury. It is the reason factorial designs are efficient. To verify orthogonality in the cracker design, we compute the dot product of every pair of coded columns, not just the 3 main effect columns, but also the interaction columns formed by multiplying pairs and triples of main effect columns. There are 7 columns in total: x1, x2, x3, and their products x12, x13, x23, and x123. The claim is that every off-diagonal dot product equals 0. Let us confirm that for the temperature and time columns as an example. Multiply corresponding entries of x1 and x2 across all 8 runs and sum. If the design is orthogonal, that sum will be 0. The dot product table confirms it completely. Every diagonal entry equals 8, that is the number of runs, and it equals 8 because each column dotted with itself gives the sum of 8 squared values, each equal to 1. Every off-diagonal entry is exactly 0. This is not approximately 0, it is exactly 0 because the design is perfectly balanced. For the client, this means each effect estimate is clean and uncontaminated by the others. The estimate of the temperature effect is not distorted by whatever fat content does, and vice versa. You can trust each number on its own terms. Now we can estimate effects. A main E effect is the average change in the response when a factor moves from its low level to its high level, averaged across all levels of the other factors. The formula is the dot product of the coded column with the response vector divided by n times 2 to the k minus 1, where n is the number of replicates and 2 to the k minus 1 is the number of observations at each level. The numerator is called a contrast. It is the sum of responses at the high level minus the sum at the low level, because the coded column is +1 at the high level and -1 at the low level. The denominator converts that contrast into an average difference. An interaction effect is estimated the same way using the product column as the contrast vector. A positive interaction means the two factors reinforce each other. A negative interaction means they partially cancel. For the cracker data, we have 8 cell means and 7 contrast vectors, 3 main effects, 3 two-factor interactions, and 1 three-factor interaction. The denominator for each is n times 2 to the k minus 1, which is 2 times 4, equaling 8. So each effect estimate is the dot product of a coded column with the 8 cell means divided by 8 cell. This is a straightforward arithmetic calculation, and because the design is orthogonal, we can compute each one independently without worrying about the others. Here are the 7 effect estimates, ranked by absolute magnitude. Temperature has the largest effect at 7.62 raising oven temperature from 160 to 200 degrees increases crispness by about 7.5 points on average. Baking time is next at 4.38. Going from 20 to 30 minutes adds about 4.5 points. Fat content is smaller at 1.62. Higher fat gives slightly crispier crackers on average. The two-factor interactions are all small. The temperature by time interaction is 0.12. Temperature by fat is -0.12. Time by fat is 0.12, time by fat is 0.12, and the three-factor interaction is -0.12. The practical message is clear. Temperature and time are the dominant levers. The interactions are small enough that the factors act nearly independently in this experiment, but we will want to confirm that statistically before declaring them negligible. Before we look at the plots, let us be clear about how to read them. A main effect plot shows the mean response at the low level and the mean response at the high level of a single factor, connected by a line. The steeper the line, the larger the main effect. An interaction plot shows 2 lines, one for each level of a second factor, plotting the mean response against the levels of the first factor. If the lines are parallel, the two factors act independently. The effect of the first factor is the same regardless of where the second factor is set. If the lines are not parallel, if they converge, diverge, or cross, an interaction is present, and the factors must be set jointly. Always check the interaction plots first. A significant interaction overrides the main effect plots because the main effect is an average that may not represent any real operating condition. We now want to visualize the cracker results. We will produce main effect plots for all 3 factors and an interaction plot for temperature by time, since those are the 2 largest main effects, and the interaction between them is the one most likely to matter practically. The interaction plot will show crispness on the vertical axis, baking time on the horizontal axis, and two lines, one for 160 degrees and one for 200 degrees. Reading these plots together will tell us whether we can optimize temperature and time independently or whether we need to specify them as a pair. The three main effect panels confirm what the effect estimates told us numerically. Higher temperature, longer baking time, and lower fat content all increase crispness on average. The lines slope upward for temperature and time, and downward for fat. Temperature has the steepest slope, consistent with its effect of 7.62. The interaction panel at the bottom is the critical one. The two lines, one for 160 degrees and one for 200 degrees, are not perfectly parallel. The gap between them changes slightly with baking time, which is the visual signature of the temperature by time interaction. In this experiment, the interaction is small, but the plot makes the structure visible. The client can see that the highest crispness is achieved at 200 degrees and 30 minutes, the top right point on the interaction plot, and that the benefit of high temperature is slightly larger at the longer baking time. Their recommendation is to set both factors high, and the interaction plot is what justifies treating them as a pair rather than independently. Now let us return to OFAT and make the comparison precise. OFAT produces valid effect estimates only when there are NO interactions, an assumption the experimenter cannot verify without running a factorial. If an interaction exists, the OFAT estimate of a main effect is biased. It equals the true main effect plus an interaction bias term. The factorial tests that assumption rather than making it. It estimates both main effects and interactions, so you know whether the assumption of no interaction is defensible. This is why the factorial is the right tool whenever two or more factors are of interest, not because interactions are always large, but because you cannot know in advance whether they are. To make the comparison concrete, let us extract only the runs an OFAT experimenter would have observed. Starting from a baseline, all factors at their low levels, the OFAT experimenter changes one factor at a time. To estimate the temperature effect, they compare the run at high temperature with all other factors at baseline. To estimate the time effect, they compare the run at long time with all other factors at baseline, and so on. The OFAT effective temperature is simply the response at high temperature and low time minus the response at low temperature and low time. That is a difference of two observations, evaluated at a single level of every other factor. Here is the comparison. The OFAT estimate of the temperature effect is 15, nearly double the factorial estimate of 7.62, a discrepancy of 7.38. The OFAT estimate of baking time is 8, compared to the factorial estimate of 4.38, a discrepancy of 3.62. Fat content shows a similar pattern. OFAT gives 3, the factorial gives 1.62, a difference of 1.38. Every OFAT estimate is inflated relative to the factorial. Why? Because OFAT always evaluates temperature at the baseline level of time. It picks up the temperature effect at that one specific condition, not the average across all conditions. When an interaction is present, even a small one, that single condition estimate is biased. A client acting on the OFAT results would believe temperature has a much larger effect than it actually does on average and might over-invest in temperature control while undervaluing baking time. The factorial gives the honest, averaged answer. To connect the effect estimates to a formal statistical model, we need to talk about the modal matrix. The model matrix is the coded design matrix augmented with an intercept column, a column of all ones, and interaction columns formed as element-wise products of the main effect columns. For the cracker experiment with 3 factors, the model matrix has 8 columns. The intercept, x1, x2, x3, x1 times x2, x1 times x3, x2 times x3, and x1 times x3, and x1 times x2 times x3. Each column sums to 0 except the intercept. All columns are mutually orthogonal. The key algebraic consequence is that X transpose X, the matrix formed by multiplying the model matrix by its own transpose, is diagonal. A diagonal X transpose X means the effects are estimated independently, and the variance of each estimate is sigma squared divided by the corresponding diagonal element. That is the algebraic signature of an orthogonal design. For the cracker experiment, we build the full 8-column model matrix and then compute X transpose X. The diagonal entries should all equal 8, the number of runs, and every off-diagonal entry should equal 0. The variance of each effect estimate will then be sigma squared divided by 8, where sigma squared is the error variance we will estimate from the replication in the next lecture. The smaller that variance, the more precisely we know each effect. The X transpose X table confirms the structure exactly. Every diagonal entry is 8, and every off-diagonal entry is 0. The diagonal value of 8 tells us something important. Each effect is estimated using information from all 8 runs, not just a subset. That is the efficiency of the orthogonal factorial. Every run contributes to every estimate. The variance of each effect estimate is sigma squared divided by 8. In the next lecture, we will use the 2 replicates per cell to put a number on sigma squared, which will let us compute standard errors, confidence intervals, and significance tests for each of the 7 effects. The structure is now fully in place. Let us consolidate what the cracker study demonstrated. Temperature and baking time are the dominant drivers of crispness. Their effects are large relative to fat content and relative to any of the interactions. The temperature by time interaction, while small, means these 2 factors should be set jointly rather than independently optimized. The 2 to the 3 factorial answered all of the scientists' questions in 16 runs, a remarkably efficient experiment. OFAT would have required fewer runs, but would have missed the interaction entirely and would have produced biased estimates of every main effect, and a replication built into the design, 2 runs per cell, provides the error variance estimate we need to attach uncertainty to every effect, which is the topic of the next lecture. Now it is your turn to practice. A process engineer is studying shrinkage in injection molded parts measured in millimeters. 2 factors are varied: mold temperature at 180 or 220 degrees Celsius and injection pressure at 100 or 140 bar. 2 replicates are run at each of the 4 combinations, giving 8 total runs. Your tasks are: write the Yates order design in natural units, code both factors to the -1 to +1 scale, estimate the 2 main effects and the temperature by pressure interaction using the contrast formula, and sketch what the interaction plot would look like. Work through each step before moving to the solution. Here is the setup for the solution. The coding formulas are: x1 equals temperature minus 200 divided by 20, and x2 equals pressure minus 120 divided by 20. The midpoints are 200 for temperature and 120 for pressure. The half ranges are both 20. With 2 factors and 2 replicates, the denominator in the effect formula is n times 2 to the k minus 1, which is 2 times 2 equaling 4. So each effect estimate is the dot product of the coded column with the 4-cell means divided by 4. The interaction column is formed by multiplying x1 and x2 element-wise, and its dot product with the cell means divided by 4 gives the interaction estimate. The effect table and interaction plot together tell the complete story for the injection molding process. Negative effect values mean shrinkage decreases as the factor increases. So if temperature has a negative effect, higher mold temperature reduces shrinkage, which is typically desirable. The interaction plot is the critical diagnostic. If the two lines, one for each temperature level, are nearly parallel across the two pressure levels, the engineer can optimize temperature and pressure independently. If the lines diverge or cross, the combination matters, and the engineer must specify both settings together to achieve the target shrinkage. That is the central practical lesson of the factorial design, and it applies whether you are baking crackers or molding plastic parts. The factorial does not just estimate effects. It tells you whether those effects can be understood one factor at a time, or whether the factors are entangled in ways that only a joint experiment can reveal.